Previously, we have seen the capacity in case of flat feeding channel, and there are two main scenarios that we need to focus on when the receiver knows the values of CSI and both transmitter and receiver knows the distribution of CSI. And the second case is both the transmitter and the receiver, they know the value of CSI, and the transmitter and receiver, they knows the distribution of the CSI. So for the first case, when only the receiver CSI is available, so we define two capacity definitions. First is the ergodic capacity and second is the capacity with outage. And with this example, we show that what is ergodic capacity. So now if we take the probabilistic capacity for this channel based on the different channel states, what we end up with is ergodic capacity. And capacity with outage indicates that to reliably transmit the data from the transmitter to the receiver, the transmitter should send with a fixed data rate with negligible outage probability. So for this example, the transmitter will send at a data rate of 26.2 kbps with negligible outage probability. But if we say that, okay, some outage probability is desired or we can handle some outage probability, we can design some new solutions. So in that case, the capacity has now been increased to 191. That means as we are increasing the outage probability, the more capacity is allocated to the channel and the transmitter can send that with a high data rate. So what we can say is as the outage probability is increasing, the capacity will increase. And also in this case, the in receiver CSI or particularly in capacity with outage, the transmitter sends with a fixed data rate. And now when the transmitter knows the value of CSI and the receiver also knows the values of CSI, then in that case, the transmitter can utilize its functionality that it will decide whether to transmit the data or not transmit the data. So when the channel is in good state, the channel will be utilized and the data will be sent. And when the channel is in bad state, then no transmission will take place. And because of this, transmitter knows the values of CSI, we can allocate optimal power based on the channel states. And this is done by water filling algorithm. And the intuition behind this water filling is that when the channel is good, more power is allocated. And when the channel is bad, less power is allocated. When the channel is below some certain threshold gamma naught, then we should not utilize this channel. So this was the optimal strategy of allocating power to the channel. Now the next thing is there are some suboptimal transmitter adaptation policy where the transmitter uses the CSI. It knows the values of CSI, but it uses the values of CSI to maintain a constant received power. That means the transmitter maintains a fixed data, fixed received power at the receiver. So it is like it uses CSI to invert the channel fading. So that means it appears, the channel appears to the encoder and decoder as if the channel is a time invariant AWGN channel. And this policy is known as the channel inversion policy. And in this case, the power allocated is equal to sigma upon gamma, where sigma is the constant received SNR that can be maintained with the transmitted power constraint, considering this constraint. And if we try to solve this value of sigma, this sigma come out to be 1 over expectation of 1 over gamma. And channel capacity with channel inversion is nothing but equal to the capacity of AWGN channel with SNR equal to sigma. So in this way we can get the capacity, channel capacity, or we can say zero outage capacity. So this expression is zero outage capacity. And since it maintains the fixed rate over all the channel states, fixed received power, so it does not depend on whether the channel conditions are good or channel conditions are bad. So the capacity achieved in this case, zero outage capacity, is less than the Shannon capacity in case of fading channel. The next is outage capacity and truncated channel inversion. So this is also an suboptimal strategy, but an improvement to the zero outage capacity. So this is defined as we want to achieve a maximum data rate in all the non-outages channel states times the probability of those non-outages channel. So in short, in zero outage scenario, it maintains a fixed rate, but in this case, outage capacity, it tries to maximize the data rate when the channel is in the non-outage state times it multiplies it with the probability of the channel in non-outages. So with this, it implies that it will only provide a data rate when this gamma is greater than this cutoff deep fade. So when this is greater than gamma naught, then only power is allocated to the channel. And whereas in the previous case, there was no constraint on this gamma, whether this gamma is greater than 0, less than 0, or it is greater than, whether this gamma is greater than gamma naught or is less than gamma naught, it does not depend on that. It will allocate fixed rate over the channel conditions. So in this case, in case of outage capacity, the channel is only used when this gamma is greater than or equal to gamma naught. And sigma in this case is given as 1 over expectation of gamma naught, 1 over gamma. And this maximum outage capacity is defined in this particular way, where we are maximizing gamma naught and B log to 1 plus sigma times the probability that the channel is in non-outage. So with this, what we have covered the capacity in flat fading, then we have covered the receiver knows the value of CSI, the transmitter knows the values of CSI, and when the transmitter knows the value of CSI, we have seen zero outage capacity and we have seen outage capacity. And now we know what we mean by channel inversion and what we mean by truncated channel inversion.